All right, so this first one says the specific heat of water is about 2 times that of ethyl alcohol. Let's say we've got equal masses of alcohol and water in separate beakers, and they're both going to be supplied with the same amount of energy. We want to compare their temperature increases. So the formula for this specific heat would be, formula is Q equals mc delta T, where Q is the heat added, M is the mass of the sample, C is going to be the specific heat, and delta T is the change in temperature. Alright, so if we have two similar samples where one has a specific heat of C, but the other one has a specific heat of 2C, then they're going to have different temperature changes even though the same amount of energy is added to each. So let's say we add the energy by just like putting a flame underneath them. They're both going to experience a heat flow of what's called Q. So okay, for the one, it's going to be delta T equals Q over MC. Okay, now that could be for the ethyl alcohol. And then for the water, we'll do the same calculation. Same heat, same mass, but this time the specific heat is 2C. So this just shows us that the delta T of the water is going to be 1/2 of the delta T of the alcohol. And that's common for water. It's got a really high specific heat, so you could add a lot of energy to it and it won't change its temperature as much as other substances, you know. So that one doesn't require too much math there. The next one's got some more concrete numbers to work with. It says a 20-gram sample of copper is at 50 degrees Celsius. If 500 joules of energy is added to it by heat, what will be the final temperature of the copper? Alright, so for that, we just want to use that rule, Q equals mc delta T. Our 500 joules is going to be our Q, and we have to look up the C of copper, though. Alright, so I'm just going to go to Google. I'll just search for the specific heat of copper. Okay, it's saying that the specific heat of copper is 0.385 joules per gram degree Celsius. So I'll just plug in everything I have. 500 joules, 20 grams, specific heat of 0.385 joules per gram degree Celsius. And then for our delta T, I'll do T final minus T initial. And they did say that the initial TI here is, TI is 50 degrees. Alright, that's an equation that you'd want to just solve for the final temperature. I'm getting 115 degrees Celsius. Alright, so the next one's similar. There's going to be a exchange of heat. Alright. Next one says 100 grams of lead at 95 degrees Celsius is placed in an insulated container holding 100 grams of water at 15 degrees Celsius, what will be the final equilibrium temperature? So to do this, the heat entering the cold substance plus the heat entering the hot substance is supposed to add to 0. But really, heat's not going to go into the hot. It's going to leave the hot. So what that means is that this will end up being a negative value. And this will end up being positive, and they just cancel out. Another way to write that is that the Q of the cold has to equal the opposite of the Q of the hot substance. That's just an expression of exchange of energy, conservation of energy. All right, so we just replace the Q's with M, C, delta T. And the cold substance was the water, so I could put like a little subscript of W on there. And then we want to do the same thing for the hot, but the hot was the lead, so I'll just put L for lead. Okay, so we'll plug in the different things and solve. Our mass of water is 100 grams. The specific heat of water is 4.186 joules per gram degree Celsius. The temperature of the water will change from 15 to some unknown final temperature. I don't know what the final temperature is, so I'll just leave it as a variable. Move all this over. Okay, then we put in the mass of the lead, 100 grams. And we'll put in the specific heat of lead, which I do have to look up on a table or google.com. It's 0.129 joules per gram degree Celsius. And then we'll do T final, because they're going to reach an equilibrium temperature, but this one started off at 95 Celsius. It takes a little bit of algebra to solve it. I get 7505 on the one side. And 431.5 TF on the other side. Therefore, I'm getting 17.4 degrees Celsius. Yeah, 17.4 degrees Celsius is what I get for the final equilibrium temperature. And I mean, one reason for that is the specific heat of water is so much larger than the specific heat of the lead. So it's just very easy to change the lead's temperature to make it come closer to what the water's temperature was. So that'll do it. Number 4 is going to actually be very similar to the one I did. Okay, so let's see. I looked up the specific heat of aluminum and mercury. So according to Google, the specific heat of aluminum was 0.89 joules per gram degree Celsius. And then the C of mercury, which has the letters Hg, is 0.1395 joules per gram degree Celsius. So we just want to plug into the equation. we've got 90 grams of aluminum. So MC, and then our delta T will be TF minus 10 degrees. And then we can just we'll add in the mercury, which is 200 grams, 0.1395 joules per gram degree Celsius, and then TF minus 120. Now, if I add them both together, I should set the results equal to 0 so that we have conservation of energy. And then I would just solve that for the final temperature. I think this time I'll just do it using an online calculator for speed here. Just letting X stand for my unknown in the online calculator. It's telling me that the final temperature is about 38.4 degrees. So this answer over here had said perhaps 37.8. They may be using a slightly different value for the specific heats. So that's what would account for the difference. The last one is how it would often be done in a lab, where you include the calorimeter as part of your calculation. So it says, in an insulated calorimeter, we assume that the sum of the heat flows is going to be 0, so there's conservation of energy. There's an aluminum calorimeter with a mass of 100 grams containing 250 grams of water. So this is aluminum, and then there's water. And then the calorimeter and the water are both at 80 degrees initially. But there's also going to be a 50-gram piece of an unknown material in the water, and that is initially at 10 degrees, but eventually it'll reach equilibrium. So the heat flow into the aluminum plus the heat flow into the water plus the heat flow into the block, they have to sum to 0. That's what this sigma Q equals 0 means. Let's see which ones are positive, which one's negative. So first of all, the block is at the lowest temperature. So what's going to happen, according to the second law of thermodynamics, is heat is going to flow into that block. So this is going to end up being a positive value. And we can show that with like an arrow showing that this is going to be the direction of the heat flow into the block. But that means that the aluminum and the water, they will have negative heat flows, which just means that heat will flow out rather than in. So we just replace each of them with their formulas. So M of the aluminum times the heat capacity of the aluminum times the delta T of the aluminum. Then we'll do the mass of the water times the C of the water times the delta T of the water. We'll have the mass of the block, I'll call it B, and then the heat capacity of the block, and then the delta T of the block. They all have to add up to 0. So plug in everything we have. There's going to be one unknown, which is going to be the specific heat of the block. So our mass of our aluminum calorimeter is 100 grams. Specific heat of aluminum, we said before, was, where is that, aluminum, oh, right here, 0.89 joules per gram degree Celsius. The final temperature, it says, was 70 degrees, so that was measured by a thermometer, so we'll do 70. And then the initial temperature of that aluminum was 80. When it comes to the water, it was 250 grams of water. Specific heat of water is 4.186 joules per gram degree Celsius. Final temperature is again 70 minus 80. Okay. Then for our block, we say it's a 50-gram block that's here. And it was initially at a cold temperature of 10 degrees. We don't know its specific heat, so we're going to solve for that. But it did reach a final temperature that matches with the other objects of 70 degrees. And now we just have to solve this equation for the unknown specific heat C equals 0. .7. It's telling me the specific heat would be 3.79 joules per gram degree Celsius. Well, if I go back in to do my check and like plug this 3.79 in here, I get that it was an addition of 11,370 joules of heat flow into the block to warm it up. And then you can check the other one, like 250, 4.186 times 70 minus 80. I get negative 104.65 joules was taken out of the water. Most of the energy came out of the water, it looks like. We'll see how much this aluminum contributed. Just 890 joules flowed out of the aluminum. So we want those, if it checks, we want those to add up to 0. And yeah, it looks like it does. Just a little bit of rounding may make it slightly different, but yeah, looks like it checks.